SwayamPrabha. Digital India. Educated India.
Hello and welcome to this Manufacturing Systems Technology Part 2, Module 3. We were talking about how to introduce quality at the product design and the process design stages itself. And as we know that, so far what we have discussed is that the product design is kind of a prime activity in the process of realizing a product, and therefore it has a great impact on product quality. In fact, it has the greatest impact. So the design is such that it is quite robust, then it can be able to allow very less non-conformance at the process and the product level. Okay, so the loss of quality really occurs when there is a deviation of the functional characteristics of the product from the target values, and the design issue is about choosing these functional characteristics and how much allowance or tolerance can be given in the functional characteristics given the aspirations or the need of the customer. And this has to be then translated in terms of the design, okay, the design of the particular product. So, the philosophy of product design kind of was changed by Taguchi, who proposed a philosophy and methodology for designing quality into products and processes. So, Genichi Taguchi was actually a child engineer by training, but he worked for the electrical corporation, ECL, in Japan, and he was actually a converted statistician, and he tried to develop some methodologies for doing quality analysis, etc. Later on, his methods were very popular in the West, and in fact he was in advisorial role for several companies for a long time, including Bell Labs, Boeing, Xerox, so on and so forth. So Taguchi basically was the first proponent of that can design be made in a qualitative manner, okay, or can process design or product design be made in a qualitative manner. So he postulates that the process of designing a product or a process should be viewed at three phases. One is the design at the system level, then the design at the parameter design level or design at the parameters level, and then the design finally of the tolerance to the parameter that has to be. So he basically organized the thought process of how to incorporate the design changes in a particular design. And there, when he means, when he talks about system design, it is the process of applying scientific knowledge to produce a basic functional prototype design. Now, in this phase, new concepts, ideas, and methods are synthesized to provide new or improved products to customer. And that means that the basic design concept is established during the phase, including the selection of parts, materials, subassemblies, so on and so forth. For example, let's say the following question related to an automotive assembly can be addressed very well at the system design level. For example, one can say that should the internal combustion engine be made out of aluminum or cast iron, should the brakes be having this additional safety of anti-lock braking kind of system, so these kind of basic questions related to the basic materials used or the subassemblies used in the design has to be addressed at this system design level, and the relationship between the inputs and the outputs would be established this way, and also the functions of the parts and subsystems are determined during this phase once the system design level questions are addressed in the quality planning. Okay. So the next stage obviously is the parameter design. So obviously, as the name suggests, the level for products process design parameters are set to make system performance less sensitive to the causes of variation, thus minimizing quality loss. So choose the parameters, the basic parameters. For example, in the case of engines, BHP or engine RPM can be a very good parameter. Okay, so choose the parameter in a way so that there are minimalistic variations in the parameter, and the capacity of the particular engine is always kept on a to deliver a parametric property or maybe a performance parametric should always be kept on the overside just by a little bit, so that always there is a compliance to the performance metrics. There should not be a situation when the metrics is at a borderline and the product is not able to achieve the metrics in most of the cases. Okay. So, plan the performance metrics in a manner so that within the capacity or the range of the product the metric lies somewhere. And in the parameter design, wide tolerances on noise factors are assumed to allow low manufacturing cost, as it is costly to control noise factors. So, obviously the parameter design stage should account for these factors where there is no control, okay, on the responsible factor contributing to the non-conformance, and these are called so-called the noise factors. And so, you have to design the process in a way so that these noise factors are addressed and very tight control is kept at that particular level. And obviously, if you on one hand allow low manufacturing costs, it means that you do not have much control on the noise factors at that particular level. So, on one hand you have to address that issue, and other hand you have to address the controlling of noise factors so that there is performance compliance every time that issue. So, there is a sort of a trade off, at the parameter design stage itself, which has to be obtained by a quality engineer at that stage to necessitate that a certain standard of quality be met by the particular product. So, during the parameter design phase, the quality is improved without controlling or removing the cause of the variation. And during the so then you can do design of experiments, simulations and optimizations, and various other techniques at this particular parameter fixing stage, so that you have the right choice of the parameter in the particular design. Then we talk about tolerance design, which is one step ahead of the parameter design, and it usually follows the parameter design phase. So, obviously, if you introduce a tighter tolerance regime, there would be overall quality improvement, because then the process selection will also have to be done in a manner so that the tight tolerance of the particular specification has to be met and at the process level. Okay. So, you have to obviously choose the tolerances around the target values, very close to the target values, so that there is a marginal difference in the output from the parameter which has been designed in the earlier stage, which can be treated as allowable for the particular quality system. Okay. And however, with the quality improvement, reduction in quality loss, which is commensurate with this quality improvement, there may be an increasing manufacturing cost because of the additional imposition on the process to maintain a tight standard, okay, of the process. So, tolerance design is basically followed at the level 3, okay, of the system design, the parameter design, and then finally the tolerance design stage of a quality design process. So, having said that, let us now mathematically try to find out what Taguchi really means by the quality loss. So, if you look at two concepts which were rather traditional, and then after the introduction of the Taguchi's concepts of design, you can find out that in a traditional system of quality monitoring, you had something called a lower specification limit and upper specification limit, and the target value would be somewhere between these LSL and USL, and any product which was lying in this particular range between the two tolerance limits would be accepted as a product. Okay. But for the first time, Taguchi proposed that this is something like waiting up till a non-conformance has happened and taken a corrective action. Okay. So, this is something like a sort of a breakdown maintenance kind of a situation, where there is an equipment which has broken down already, and then you have to figure out what is the cause. So, you cannot wait up till the process goes out of hand or out of the USL or the LSL specifications. So, therefore, any deviation from the target has to be somehow met to be some kind of a indicator, which in this particular case is known as the quality loss. Okay. And this indicator would be so stiff that there is any variation from the target, you should be recording as the square of that variation the loss factor which comes into picture, so that at a very early stage of the process going out of control, you should be able to, before the process goes out of control, you should be able to report that yes, there is a possibility for the process to go out of control by looking at the loss figures, okay, and looking at the variations from the target, and that is how the whole philosophy is incorporated into the particular matrix, okay, or particular quality framework. So, here for example, if I was talking about a shaft diameter having a value of 1 plus minus 0.03, meaning thereby the design spec says that the shaft can go between 0.997 to 1.03. The question is, why to allow the process to continuously produce something at 1.01 level or even at 0.998 level, which is still within the upper and the lower specification limits. Okay, but it should definitely contribute to an indicator which is merely a virtual indicator of a loss, where this loss then can be philosophically managed with some countermeasures, some decision making on the part of the administration, so that it comes back to 0 now. Okay. So, that is what Taguchi's loss function talks about. So, obviously, T is the target, Y is the value of the quality characteristic which is there. So, Y minus T is really the deviation from the target, and you are basically mapping the loss as the square of that deviation from the target. And loss typically is mentioned in currency units, so that every design specifications non-compliance is now mapped as a loss, indicating what it is away from and how much away from it is going. So, therefore, if you can set up a separate tolerance range for a process control from the design specification range that has already been available, you should not even allow the process to go out of the process tolerance range, which is much within the design specification range. So, therefore, in almost 100% of the situation, there would be a complete conformance to the particular attribute, the parameter design attribute with the tolerance attribute which has been proposed at the design stage. So, that is how you mention the quality loss. So, obviously, we do some statistical analysis here to see what this loss can be really computed as, or how to control this loss, and then try to do some realistic examples where we will use this loss factor to identify things related to the process. So, obviously, let us say there is a process where this yi represents the ith measurement of the quality characteristic. So, the average quality loss can be computed as obviously the summation of all the different losses divided by n number of losses. Let us say there are n such representative measurements of the quality characteristic y which has been obtained. So, the overall average loss would be the loss because of y1 away from the target, loss because of y2 away from the target, y3 away from the target, so on and so forth, yn characteristic away from the target. Okay. And so, this can be plotted as k by n times of y1 minus t square plus y2 minus t square plus y3 minus t square plus so on and so forth up to yn minus t square. And we can actually in a very convenient manner represent this, because we can probably think of doing some manipulations here. So, let us say if we gather together these values, you have y1 square plus y2 square plus y3 square plus so on and so forth up to yn square. Okay. And then you have minus of n t square, there are exactly, I am sorry, plus of n t square, there are exactly t square values which are emanated here. And then you have minus of twice t times of y1 plus y2 plus y3 plus so on up to yn. Okay. And so, in a way, what you are trying to calculate here is related to, we can just manipulate this whole equation that has been formulated to have realistic values in terms of the significant parameters for any such statistical distribution like the mu and the sigma, the mean and the standard deviation. So, let us see how. So, we are now sort of adding, and so we supposing we take the n value inside, we have the first term represented as y1 square to yn square by n plus nt square by n, meaning thereby t square, minus of you have twice t divided by y1 plus y2 plus so on and so forth up to yn divided by n. Okay. And as we can probably see from here, you have a possibility of introducing the mean characteristic quality characteristic mu, which is actually y1 plus y2 plus so on up to yn divided by n. Okay. in this particular way. So what I would rather prefer to do here is sort of calculate by adding and subtracting the values minus mu square and plus twice mu times of 1 y1 plus y2 plus y3 plus so on so forth up to yn divided by n here, so that I can actually write this down as y1 minus mu square plus y2 minus mu square plus yn minus mu square divided by n, okay, plus square of t minus twice t y1 plus y2 plus y3 plus so on up to yn divided by n. Okay, so that's how I can write the value of the average quality loss AQL as I have been computing from before. Okay, so how this term comes in is simply that if you open these square brackets, you will be left with y1 square plus y2 square plus y3 square plus so on up to yn square minus of plus of mu square, because there are n such mu squares together and divided by n makes it mu square, and minus of twice mu times of y1 plus y2 plus y3 plus so on up to yn divided by n. So what I am essentially doing is subtracting and adding the same terms here to this, so that effectively this all can result in only this term y1 plus y2 square plus so on up to yn square by n. So having said that, I can write this down as a full expression y1 minus mu square plus y2 minus mu square plus so on so forth up to yn minus mu square divided by n minus of mu square plus twice mu times of y1 plus y2 plus y3 plus so on up to yn divided by n. Obviously there is a t square plus twice t times of this y1 plus y2 plus so on up to yn divided by n. Okay, so I am left with finally a situation where this actually is mu, right, and so is this, and I would be enabled with k times of y minus mu square plus y2 minus mu square plus so on so forth yn minus mu square divided by n minus of mu square plus twice mu square makes it plus mu square plus t square minus twice t mu. Okay, so I can say that this is equal to k times of y1 minus mu square plus so on so forth up to yn minus mu square plus I can write this as mu minus t whole square. Okay, and this is divided by n. So that's how I can write the average quality loss as is. Just sort of pull out all the values together so that I can write the AQL in a more appropriate manner. I can say that if I look at this particular value here, this is nothing but yi minus mu square sigma, again probably sigma varies between I equal to 1 to n divided by n, right. So I can make this look like sigma square. So if I supposing we already know that sigma square here, or maybe just the square of the standard deviation is represented statistically. So this sigma square can be represented as 1 by n minus 1, sigma I varying between 1 to n yi minus mu square. So I can write down this whole term as n minus 1 divided by n sigma square. Okay, so that's how I can write this whole term. So obviously then the AQL becomes equal to, from the last term it was equal to n minus 1 by n square of sigma plus mu minus t square. So, that is how you can record the average quality loss. Now, the question is whether really this is the average in and there are some quality parameters which are desirable and there are some quality parameters which are undesirable. For example, let us say if we are talking about vibration and noise in an equipment, that is something which is sort of undesirable parameter vis-a-vis a parameter where you are talking about, let us say, the dimension of a shaft. So, when we are talking about a quantitative parameter like the dimension of a shaft and how much away it is from the target, the average quality loss probably makes sense. But when we are talking about an undesirable characteristics like say friction and wear, where the minimum possible the better it is, in that kind of a circumstance it becomes a little difficult to understand this as the deviation from the target. So, we will close this lecture here in the interest of time, but in the next lecture we will probably try and see if we can do something with this AQL so that it can change contextually to what is the kind of parameter that we are discussing. Thank you.